Hello, young scientists. Have you ever wondered how the salt you sprinkle on your food gets its structure? It's all thanks to ionic bonding. Ionic bonds are one of the most fundamental ways atoms come together to form compounds. Imagine sodium, a metal, with just one electron in its outermost shell. It's eager to give up that electron to become stable. On the other side, chlorine, a non-metal, is looking to fill its outer shell with an extra electron. When sodium loses that electron, it forms a positive ion, Na+, and chlorine gains that electron, becoming Cl-. These oppositely charged ions are strongly attracted to each other, and that's what forms an ionic bond, like in sodium chloride, table salt. It's nature's way of achieving balance through electron transfer.
Let's take a closer look at how ions are formed. Sodium gives up one electron, and this process requires energy. This energy is known as ionization enthalpy. When sodium becomes an A+, it has a full outer shell, just like the noble gases, very stable. Now, chlorine steps in, eagerly gaining that electron to become Cl-. This is where electron gain enthalpy comes in. When chlorine gains the electron, energy is released, making the process exothermic. So, you've got sodium losing an electron in an endothermic reaction and chlorine gaining it in an exothermic reaction. When these ions meet, they form a stable ionic bond. It's all about energy balances and the quest for stability. Now that we understand how ions form, let's explore the role of lattice enthalpy. The lattice enthalpy is the energy needed to separate 1 mole of solid ionic compound into its gaseous ions. Think of it like this. Imagine trying to break apart a huge, tightly packed crystal of salt. It takes a lot of energy, but that energy is released when the ionic bond is formed, stabilizing the compound. For example, the lattice enthalpy of sodium chloride is 788 kilojoules per mole. This shows how strong the bond is in the crystalline form of sodium chloride. And even though ionization is endothermic and electron gain is exothermic, the lattice enthalpy more than compensates for the energy absorbed during ion formation, making sodium chloride incredibly stable. Ever wondered what an ionic crystal looks like? Picture this. In sodium chloride, NaCl, the ions are arranged in a neat repeating pattern. This pattern is called the rock-salt structure. Sodium ions and chloride ions alternate in 3 dimensions, and each sodium ion is surrounded by 6 chloride ions and vice versa. This regular arrangement is what makes the structure so stable and gives sodium chloride its solid form. The number of oppositely charged ions surrounding each ion is known as the coordination number, and in sodium chloride, that's 6. It's like a well-organized community where each person has 6 neighbors, ensuring everyone is balanced and stable. Not all ionic bonds are the same. Some are stronger than others. The strength of an ionic bond depends on 2 things: the size of the ions and the charges on them. The smaller the ion and the higher the charge, the stronger the ionic bond. For example, magnesium oxide has a much stronger ionic bond than sodium chloride because the magnesium ion, Mg2+, is smaller and has a higher charge than the sodium ion, Na+. This means that the attraction between the ions in magnesium oxide is much stronger. The strength of these bonds also determines the properties of ionic compounds, such as high melting points and solubility in water. Ionic bonds are everywhere in nature and industry. Take sodium chloride, for example. It's more than just the salt on your table. In biological systems, ionic compounds like sodium chloride help maintain the balance of fluids in and out of cells, and they're crucial for nerve function. In industry, ionic bonds are used to produce fertilizers, chemicals, and even to purify water. Ionic compounds have wide applications because of their strong bonds and stability. For instance, sodium chloride is also used to de-ice roads in winter, showcasing just how important ionic bonding is in both the natural world and our everyday lives. Let's quickly review what we've learned about ionic bonding. Ionic bonds are formed through the transfer of electrons, creating positively and negatively charged ions that attract each other. The strength of these bonds is determined by lattice enthalpy, and ionic compounds have unique properties like high melting points and the ability to conduct electricity when dissolved in water. Whether it's the salt on your dinner plate or the essential role they play in our bodies, ionic bonds are at work in many aspects of life. I hope this session helped you see how ionic bonding is not just about theory, it's the chemistry behind the things we encounter every day. See you in the next class for more fascinating chemical reactions.